Hello, this is Circ05 C Attempt. My name is Christian Williams. Date is October 20th of 2021. This project, or Circ5, is focusing on a shift register, which is a integrated circuit that we can use with our Arduino. The advantage of using integrated circuits like this is it frees up pins on the Arduino board and each integrated chip that does an independent task by itself as a component in the circuitry rather than a component in the program. Um, uh, this particular one is shift register. With what we've been using it so far, essentially can count up in binary. Although I've been led to understand that the chip can also be used for other purposes, but in this project, basically it's a binary counter. Binary being base 2. Humans, or currently we count everything in base 10, so we go up to 9, and then we go to 10, which is a 1 in the tens place and 0 in the ones place. And then when we get to 99, we then go 1 to the hundreds place, 0 in the tens, and 0 in the ones, and so on. Binary, it's just 2, so that's where we get the 0, 1, 0, 0, 1, 0, 1 kind of way of storing data, which is useful because those values are switches or transistors. So the code here for the C attempt, if I scroll all the way to the top here, similar to the other C attempts, there's a lot of stuff in this program. A lot of it's copy-paste. The program itself is only running one particular thing once we actually input it to the Arduino board, but we have all the code in one place so we can manipulate it and learn from it and do various things. So what we are specifically doing for this one is first we have to set up integers. The integrated chip has 3 ports. One which is for taking in data, one that is for taking in a clock, and one that is for taking in latches or understanding that. All 3 of those are output, and this is the information that the Arduino feeds the integrated circuit, and that integrated circuit then takes that information and completes its task. If we're doing specific LED manipulations, we also have these integers to pull in as well. But again, depending on which part of this program we're using, those integers may never be used. And then for a void setup, you're probably used to all the pin modes being sent to output. In this loop here, I did one slight change just to make it a little bit more obvious of what's happening on the board. I changed the delay time to 1 second between each LEDs instead of 100 milliseconds, just so it's a little easier for us to understand what's going on. Otherwise, we're using a for statement to increase the value each time by 1, starting at 0, and it will stop at 255. In actuality, there are 256 values in this setup, with 0 being the first value, which is why we're saying less than 256. And that'll come into play a little bit more if you understand how binary works. We basically have 8 positions that we're using with the 8 LEDs, so using that exponential value for the final binary position would be the 8, or 256. If that didn't make sense, don't worry about it. I'm still learning it myself. Then we scroll down and we have 2 parts of our program. C is going to be using this one. C attempt is using this. In the B attempt, we'll be using this. So for now, I'm just going to explain what the first one is. So all we're doing is we're updating each of our LEDs, and this is a more concise way of doing it than in B attempt. And it is going to be taking the chip and setting everything to 0 or low, and then kind of shifting out based off of clock value and so on, the 8 bits to the shift register so it knows what to do. And then it'll, of course, digital write our latch to high, which will help display the data. So again, we're not going to do this quite yet. And what that looks like in principle, all this fancy code, again, I understand I'm brushing past it, but I'm still kind of getting used to it, is this chip in real life, which I just reset, so you'll see it. And you can see it is counting up in binary. Turning it sideways might make it a little easier to understand what's going on. So this LED is responsible for 1, this is 2, this is 4, this is 8, 16, 32, 64, 128. So when we're counting, if I reset it again here, I'll just kind of convert it very quickly. We have 1, 2, 3, 4, 5, 6, 7, 8. That is how this board is counting up to 8 using binary. And you could see it kind of shifted along that value here, and it just counted to 16 right there with that light turning on. Wiring wise, you kind of saw the shift register board up there. So we have basically this integrated circuit. This is our shift register, and you can see just the 3 pins being used there, feeding the necessary information into the Arduino. So all of them are set to output, so the Arduino is talking to the chip, and the chip is just doing its math based off of those values to turn on these 8 LEDs. So in a previous project where we were controlling 8 LEDs, we had to use at least 8 of these pins in order to do that. Because we have this, and as long as we're doing tasks similar to this, we only have to use 3, and we can use this integrated circuit. That's the advantage of this circuit. Otherwise, powering up is the same. Resistors here just to make sure nothing, no LEDs burn out. As you can see, we have those 2 red cords at the top. That's making sure that this column is powered up. And that's to get the most space out of our board as possible, since the integrated circuit, this little bridge in the center breaks those parallel bands in half. So we basically, if you want to think about it, we have 2 boards, for lack of a better term, thanks to that little channel. And that, yep, so you can see all the LEDs. There's nothing too fancy wiring-wise. We're not using any buttons or potentiometers or anything to control the input, so it's just running a program all by itself. So yeah, that's basically it for the C attempt. The B attempt, as I mentioned, will go a little bit more into another function of this code here, to basically do things the hard way. So I will see you in the B attempt.